office hours stream for Monday, October 5th. Let me log in to Twitch here to so that I can also get questions and so forth. Why is it showing me as offline? Nope, I'm good. Awesome. Okay, now I'm on Twitch. 0 viewers. It's time for office hours, right? Yeah, awesome. It's cool. We just... Oh, nice. 13 viewers. Just took a little while. Perfect. Okay, what else do I need to do? I need to post on Twitter. Boom. Okay. Cool. Let's get started. Anyone got questions about memory corruption, memory errors? Oh. Okay. We have a question on number 9, number 12, number 8. So let's go in order. And number 11. So let's start with 8. Let's take a look at what 8 is. Let's take a look. Challenges. Oh. Level 8. Alright. Run it in practice mode. And let's open it up in Binary Ninja. And then let's log in here. Awesome. Okay. So, level 8 has no canary. Awesome. It's position independent. And let's just see what happens when we give it a very large payload. Okay, so we say we want to send a payload. It has, we overwrite, awesome. So then we write enough to, let's get a cyclic pattern in here. Actually, let me do this in a screen session. Okay. Let's get a 1,000 byte long cyclic pattern. Run this in GDB. Awesome. We run it. Payload size, give it 1,000 bytes. Paste in our cyclic pattern. And we hit an assertion, which is that the string length is less than 41. Okay, so now something is tricky here, obviously. Let me just run it directly. Oops. Let's get that cyclic pattern again. String length is less than 41. That's the assertion. let's take a look at what a testing version of these looks like in Binary Ninja. And we'll see what's going on. All right. So, of course, as in all of these, main disables buffering and then calls vuln. Vuln disables buffering and then gets the payload size. Right, let's take a look at this in decompilation. So it roughly speaking, it says send your payload size. It gets the amount that we read. All right. Reads from the file descriptor. Then it makes sure that the string length of the buffer, right, is less than 6B. That was it's a different size in the testing and the teaching, but that's our maximum size. If it's greater than that, then it prints this assertion fail. Otherwise, it memory copies from our buffer into another buffer. This one's on the stack, whereas this first buffer is on the heap. So here is first buffer. Okay. So the read happens into the first buffer, then it gets checked for the string length, and then it gets copied into the stack buffer. All right. The question is, how do you solve this? One student emailed me saying, hey, I'm trying to do a heap overflow, and I just don't know much about the heap. For sure, you should not be looking at overflowing in the heap for two reasons. One is, that's a later module. We'll be doing that in a couple of weeks. Two, if you look at this, this is the scanf for the payload size. This is our payload size. We allocate exactly enough for the payload, and then we read exactly the payload size. There's not an overflow there. There's no heap overflow. Even if there was, aside from like that second level where it's just a trivial thing where you just have to line up the memory addresses, and there isn't going to be complex heap vulnerabilities in this module, of course. Second of all, it's not vulnerable, right? So then that leaves, if this all looks correct, let's say it looks correct up through here, right? We have the payload size, it's exactly correct. Then there might be something wrong here, and that is true. Of course, it's not going to be with the puts. There's something wrong here. Okay, so we're narrowing it down more and more. Sorry, I should have strove to eat my cookie before this started. We made very good coconut oil based instead of butter. What's it called? Oatmeal raisin cookies. They're super good. All right. Anyways, so there's something. A bug arises between this line and this line, right? And specifically here, we use strlen to make sure that the length is small enough. Here, if the length is small enough, we copy the first buffer into the second buffer. And we copy, in terms of the amount of the buffer, we copy this amount read amount of the bytes. Right, so what is that? That is the return value of read. And what is this? This is something else. Here we're calculating the length of the string that you read in. So how can you cause a discrepancy between this and this. That's the way to approach level 8. Awesome. On Twitch, we just got a question. What am I looking at? I'm looking at level 8 testing 1 here. So yeah, it's basically the discrepancy between this size check and this copy size. The hint is that's vulnerable. You can overflow the buffer here. That size check is not correct. Yeah. Oh, the other hint I would say is it's not about sending a gigantic string. You might say, based on previous levels, based on level 5 specifically, that, hey, what if I send a string so big that strlen overflows and returns 0? That's going to be an extremely large string. Technically speaking, maybe you could have done it on a 32-bit platform. On a 64-bit platform, it's not going to happen. You can't fit that many bytes in memory. Even though memory addresses are 64 bits on a 64-bit machine, for hardware architectural reasons, you can only really fit about 48 bits worth, 2 to the 48th of memory, even if you have that much RAM, right? Cool. Okay, so that's what I'll say about level 8. Let's take a look at level 9 real quick. We had a question about that. Start up a practice mode. Connect up. All right. Prints out a lot of stuff. But the key thing here is this paragraph. All right. In level 9, canaries are enabled, right? So normally this means you're screwed in a stack-based overflow in terms of trying to overwrite the return address. But here, there's a looped one-by-one input. This sometimes happens. For example, it happens internally in a lot of variable length network protocols. Or it happens not as a read, but as a byte-by-byte copy. And what happens basically is there's a couple of new lines missing. That's a little sloppy on our side. We're iterating. We're reading 1 byte at a time, right? And until we have read the total number of bytes we want to, we keep incrementing this index into the input buffer, right? So let's take a look at what this looks like in Binary Ninja. If you look at, let's look at one of the testings. They're, of course, easier because of fewer printfs to go through. Okay. Let's take a look. So, here's the read, here's the loop. Okay? Let's look at the read. The read takes a couple of arguments. EDI is the file descriptor number. So this is obviously the file descriptor. For us, it's standard input here. All right, that's nice and easy. Second argument is the buffer. And it goes from RCX. Okay, it's RDX plus RAX. RDX comes from EAX here. EAX comes from what is stored at RDX, RAX. Wow, so this is pretty confusing. But here we can kind of see a slightly different approach. Let's look at the while loop. Actually, let's do this. Let's look at it in decompilation. here is our buffer, or our looped read. So we go through and we read, it doesn't synchronize the names. Okay, file descriptor here. Here we have our, this looks like some sort of pointer plus this var 98, which is also a pointer somewhere. And then var 90 seems to be the, yeah, so var 90, while var 90 is a pointer to our counter. While the counter is less than the size, and this is the size where the target of scanf, right? So this is our payload size. We say payload size, and then we do the scanf. Okay, and while var 90, or the data that is there at var 90, because it gets dereferenced, is less than the payload size, we keep looping and reading. So this is our amount read so far. Let's rename that to be shorter because that doesn't fit. Bytes read. This gets dereferenced and added to var 98, which is a pointer to var 87, which is a buffer on the stack. This is the highest level layer. It's a little hard to read. So let's go back to the disassembly. Hopefully the yes, okay, perfect. All right, so we got bytes read here. That we switched to the. Oftentimes when reverse engineering this stuff, you can jump back and forth between the disassembly and decompilation because certain things are easier to look at as a compiler, and in the compiler, certain things are easier to look at in the decompiler. Sorry, other things are easier to look at in the disassembly. For example, the specific way that data flows through memory here is easier to look at in disassembly, but on the high level, we were able to look at the decompilation and name some of these variables, right? So what we are left with is this var 98. The only thing missing out of here is the buffer, so it looks like var 98, something is stored here, it gets moved into RAX, aha, and then we load effective address of that plus RDX, and RDX is originally coming from this bytes read, so this is our buffer. So we get the buffer, and we index into it with the amounts of bytes we read, and then we call read. And how much did we read? We read RDX amount, which is 1, right? So we read 1 at a time, and we keep reading. So now let's see what is going on in terms of how this works. So our buffer is located at a pointer to our buffer. Sorry, is located because this gets read into REX, so it's dereferenced. So this is pointer to buffer. Okay, so the pointer to our buffer is located at RBP minus 90. Let's see where this pointer. Okay, this pointer is stored right here, and its REX is stored into it. And REX is the effective address of var 78. So this is where our buffer is. So var 78 is RBP. Wait, was it var 70? Whatever, it doesn't matter. RBP minus 70 is our buffer. Then RBP minus 90 to the left of our buffer is the pointer to our buffer. So if our buffer overflows, we won't touch the pointer to our buffer. What can we touch? Right, let's take a look. For one thing, bytes read isn't actually the bytes read, is the pointer to bytes read. And that is at remove REX, remove REX into that to initialize it. REX is 5C plus REX, and originally REX was the address of our buffer. So it looks like the amount of bytes read is 5C into our buffer, right? So our buffer, we have a buffer that's size hex 5C, and then it has the amount of bytes read right afterwards, right? So when we overflow the buffer, we immediately overflow into the amount of bytes that are read, right? And that's how you solve this level. Think about what happens when you start overwriting this as it is being written to. And actually, let's run through it in GDB real quick. Let's launch the testing container. So here's what I'm going to do. I'm going to launch this in GDB. Thank you. Okay, I'm going to launch this in GDB. I'm going to break at read. I'm going to enter some commands to execute at every read. I'm going to write RSI. Sorry, let's just do all of it. RDI. That is, of course, the file descriptor. RSI, the address to write to, and RDX, the amount, which is, of course, 1. All right. Then we'll continue. Okay, so now every time we hit a read, it'll print that out. Let's put our cyclic pattern into a file here. Okay, and let's run. Oh wait, this is in a file in my home directory. Sorry, on my computer, so transfer it over there. Awesome, okay. And send it as an input here. Okay, why didn't it continue automatically? The fuck? Oh, you're right. I didn't give it the payload size. Thank you. Let's here we go. The input is going to be this is going to be annoying. Okay, we're going to run into the same problems you run into. Okay, let's do this. Then did this work? Input. Continue. Yes. Okay. It somehow did. So let's where did it? Okay, hold on. Let's disable the fancy configuration, and we'll put in my normal configuration. Okay. Gosh darn it. Okay. Break on read. The commands. Can do this, right? Commands. Let's just print out the buffer address because we know the file descriptor is standard input and the size is 1. doesn't like that. Okay, then we run. Okay. Why is it calling read so many times? Oh, here's a trick. So the problem is we're here. Let's run it and see where we're breaking. Well, it's hard to see where we're breaking, but we're breaking where it like reads in the libraries and all of this stuff. So let's do this. We disable breakpoint 1. We break in main. We put commands there to enable breakpoint 1 and continue. Cool hack. So now, okay. So now what? Why? Oh, okay. So here is where we're reading to. Here we go. This is probably the start of our buffer. Then we read to the next byte, the next byte, the next byte, the next byte. Okay. The next byte, 8, 9, A, B, C, D, E, C4, C5, C6, D2. It looks all good. We're incrementing by 1. We're incrementing by 1. Incrementing by 1. All right, now we're still incrementing by 1. We've rolled over, of course, from 7FF to 800, but that's fine. No problem there. Still incrementing. We have OC. And then suddenly we have 2.9. What happened? Well, what happened, obviously, is that we overflowed past the buffer into the counter. And that counter is used to index into our array. Right? So if we scroll up to where we started, this is the address of our buffer, right? This is what starts getting incremented. So if we say commands for breakpoint 1, now we're overriding the commands. Instead of RSI, we're going to print RSI minus this. Okay, let's do the same. All right. Oh shit, sorry. Commands. Sorry, I shouldn't have done X. X is examine. I want to print it. Size letters are ambiguous. Are meaningless. Sorry. Print it in hexadecimal. Okay. Run. Okay. Here we go. No, come on. Why didn't that cleanly... Okay, that's annoying. We're going to do something a little more clever. We're going to write a GDB script for this. Oh, we wrote a GDB script for something else, but that's okay. We don't need it now. So, you can't dump the history. That's fine. Let's do this. We're going to take a quick look at Binary Ninja Cloud. In the Walden function, no wait, this is the teaching level. This is level 8, level 9, okay. We're gonna break here the first time, save off the value of RSI, That's where our buffer is. And then we're going to save off that buffer address, and then in future iterations, we're going to print out the buffer. Okay, awesome. So we're gonna break an base plus ox2 ocb, right? Yep, awesome. Commands. We'll set the buffer address to RSI. Continue and then we'll disable, before we continue, we'll disable this breakpoint, breakpoint 1. And then here we'll break inside, we'll break also into OCB. Can we do this? Let's see. Okay, and then we will print RSI minus buffer address. This should give us the offset into the address. Into the buffer. I'm also overcomplicating it. Of course, we could also just print the value of this this bytes red guy, right? Like right here, where it. Why don't we just do that instead of being insane? We'll just break here and print RDX, which is our index into the buffer. Okay. Much easier. Let's break at base plus that. Commands. What was it, RDX or RAX? It was RDX. Oops, shit. Well, hopefully continue will kill it. All right. And then we'll run. So as a reminder, if you want to set breakpoints, so I was trying to set a breakpoint at a constant base, at an offset to a constant base address. A couple of office hours ago, we figured out that when a program is set UID, GDB cannot disable randomizations, even though when it launches it in ptrace, the set UID bit is ignored. So it's some stupid thing, but now we just have to copy it somewhere. For example, if you copy it into our home directory, all will be good. So now we do the same thing. We break here. Okay. All right. Nice and easy. Start at 0, 1, 2, 3, and let's see where it gets interrupted. So far, so good. So far, so good. A, B, C, E, F. Did I miss it already? All right, much easier. Let's just replace the input with, oops, 1,000 A's. That's not 1,000. That's 1,000. All right. Hex 40. Oh shit! Why did I do that? All right. Commands. This guy. Continue and okay. we have 1000 A's, which is hex 40. So eventually we'll see there. So we go 5B, 5C, 42. So we jump backwards into the number right after hex 40. So what happened? What happened was, at some point we overflowed into our index. And we did that right here. The read, of course, wrote into the index. That ended up changing this to hex 40. It went back here to it did this read here. Then over here, where we went back around to check, have you read enough? We are reading this number of bytes that we have read, and we just wrote over it, right? So when we do this next read, we control our DX now. So we can actually write to whatever offset we want. And that's how you solve this problem. I'll leave the rest as an exercise to the reader. Sorry that was so convoluted. Sometimes that's how it be. All right, let me take a sip of tea here. Awesome. Whole class is convoluted. Comment on Twitch. Exactly. Okay, we'll get to the philosophical questions about memory corruption in a sec. What was next? I think number 11, right? Awesome. Okay, well, let's start with number 11 and then we'll move on to number 12. Number 11. Let's take a look. Launch it up in practice mode. SH back in. Okay. Payload size. Boom. Send my payload. Wait, oh, I launched testing one by accident. One sec. Let me launch number 11, teaching one. No, what? I launched number 11, teaching one. What is going on? Oh, lol. This is the baby 9 that I copied to my home directory. Okay. Sorry. All right. Long function has been launched. Challenge stores your input in a memory mapped page of memory. So we call memory map. And so as you should recall from the shellcode modules, mmap maps a page of memory for you to use, right? So this program is calling one memory map once. Okay. Then it's calling memory map actually a bunch of times. And then, oh, I see. And this is the input buffer. Interesting. Then here is where it memory maps the flag. So if you recall in your reverse engineering challenges, one of the input modes was a memory mapped file descriptor. That's what this is. You've seen this before, right? It opens the flag and then it says, hey, actually map this flag file into memory at this address, right? So that's the address you get. then you get a bunch of others, and then here you have payload size, and this payload size is completely unrestricted. Well, yeah, I mean, it is restricted, obviously, but there. What? Why did I send -1 bytes? Anyways, there you go. Don't enter too big a number. The payload size is unrestricted, so you can send quite a long way, quite a lot of data, and the data will be written to here. So if we strace, hold on, this is an annoying situation. Oh, by the way, check out what happens when I enter whatever, this one bazillion in here. It reads it 1 byte at a time. 1 byte at a time. Looking for the first non-digit character. That's how scanf works. So keep that in mind when, you know, that is the scenario that level 9 is designed to explore. Anyways, there's no overflow here, of course, but I can send whatever data, amounts of data, and I can send enough data to overwrite the flag page. Let's run through it in GDB because strace doesn't give us that address, and I don't want to figure out how to make it do that. Let's run. Okay, payload size very large. Okay, send your payload. Let's break here. RSI is our buffer. Here's the buffer. This is exactly where this was memory mapped. And of course, the flag failed to get memory mapped because we are not running as root, and the flag is readable only by root, but we can use sudo in practice mode. Hold on. In my under root, I have what? Oh, root. Okay. Awesome. Okay, here we go. Run. Okay, break. Okay. So the flag is here. Where I'm reading to is right there. Okay. From the flag, to here, where I'm reading to, is hexadecimal 3000, and it's happily reading in. Quite a lot. That's my 11 bazillion. There. Reading quite a lot. This obviously is more than hex 3000. Okay, then what happens after I send it, and it prints it back to me. Okay, how does it print it back to me? Well, this is a matter for, let's opening up one of the testings in Binary Ninja. So here's that memory map, payload size, send your payload, and then it calls printf to print out the payload. So the key hint I'm going to give you is there are two hints. One is you can overwrite. You can write a lot, right? The length is unbounded. Two, if we do this and we give it a payload size, and now it's waiting for us, right? If we SSH in here This is where, thank you. Can't see my terminal. This is the process, right? Just waiting on my input. Okay. Cat proc 80 maps. Okay, let's see where it mapped the flag to. C000. Right here. Wonder why it doesn't hold on to this. This should say /flag. Did we delete /flag? No, it's still there. Okay, anyways. Here's where the flag is. And then it later mapped BF, BE, this is BF000, BE000, and BD00. And this is where our input is going. Here is C, and then here's BD through C is also mapped. So you have a continuous range of memory that is writable up until the flag. And then the third hint I'll give you is to look at the causes of disclosure lecture. And there you go. This is, in some sense, an inverse of level 9, of level 8, in some sense. Cool. Okay. Let's see. What was next? Was someone saying this is level 11? Okay, someone was saying level 12. Let's see, level 12. That's a big number. That sounds pretty advanced. I don't know if I can solve it. 17 solves on level 12? Look at these heroes. Amazing. Wait, how many people have solved everything? Really? Ah. 12 people have solved everything. Wow. Connor, is that more than usual? Oh, Connor's not on the Zoom. Anyways, okay. Maybe we should make these harder. Connor says it's about normal. All right, cool. So, let's launch up level 12 teaching. And see what it's about. SSHing back in. So if we run it, gives us the standard stack dump. That's pretty good. Okay. There is no win variable. So we have to execute the win function. That's fine. Binary is position independent. Okay. Payload size, very high. Okay, so this way overflows the buffer. Okay. So what's the core challenge here is we don't know the return address, right? But like this says, like the walkthrough says, the last 3 nibbles of an address are always going to be the same, despite alignment. That's the offset into a page. Remember, a page is OX 1000 bytes. If you look at, the execution of this, libc, for example, is always at a different address. But the last 3 will always end in 0. That means the 10th byte in libc is always going to be at 010. Likewise, the 10th byte of your program is going to be at 010. The 20th byte will always be at 020. The byte OX FEE is always going to be at FEE. But then there, of course, since you write memory 1 byte at a time, you have if you write OXFEE, you'll overwrite this with 0, and you have a risk of ending up with an invalid address. So let's take a quick look to make sure we're not missing something in level 12. Let's take a look at level 12 testing. It's very simple. Wait a second, am I giving a walkthrough for the wrong level? Ah, yes, there's one twist. Sorry, that was a walkthrough for a wrong level. There's one twist. The twist is that if we do a check sec, we have a canary. So it's not just that we can overwrite the end of the return address, right? Let's give this a try. We run teaching 1, payload size 1000. Send quite a lot of A's. We should crash at 41, 41, 41, 41, but that is not the case. Okay. Stack smashing detected. But the nice thing is, hey, this challenge has a trig hidden in the code. Reverse engineer it and see the hidden backdoor. So let's reverse engineer it and see the hidden backdoor. And the other thing, by the way, it tells us what we sent. All right, so we go to reverse engineering. Here's the thing. Okay, here's the you said printf. Now recall, since you'll be doing this presumably after level 11, that printf will be very significant to you. You know the flaw that this represents. And then here is the other the other thing that we need to find. So it checks. Let's look at this in high level. Okay, it looks for the string repeat in var 60, and var 60 is the buffer for read. So this is our buffer, read buffer. Okay. Looks for the string repeat, and if the string repeat is found, so if stir stir returns a non-zero value, it calls vuln again. So you get another chance at the input. So let's take a look. Payload it. Just say repeat. Boom. I can keep doing this for as long as I want, and it keeps printing stuff back to me. Putting this together with what you learned in level 11 and 10 should give you all of the building blocks you need to solve this. All right. We have 3 minutes left in office hours. I think I covered all of the specific requests for level walkthroughs. There was a philosophical question about how long memory corruption vulnerabilities are here to stay. Actually, we covered this in the extended Q&A. I'll try to find the timestamp and comment or added the description of the post. One question about level 15, can we access the server's printed output from the client? Let's take a quick look at 15. I'm launching up 15 teaching 1 in practice mode. Okay. Here's 15. The challenge is listening for connections on TCP port 1337 and you get one connection at a time. So I can netcat. It's an awesome utility. Port 1337. Okay, succeeded. Payload size 10. Hello. What's going on? Okay. And then we get a bunch of stuff printed in the parent. This is the whole walkthrough that's actually printed. Yeah. To the parent. Connection accepted. The vuln function has been launched. All of this output. Question is, okay, one question was, can we access the server's printed output from the client? No. But if you're using pwn tools, you can launch up the server in a process, pwn.process. You can connect in the same script, connect to it in the pwn using pwn.remote, and then read from both as you want. Then the follow-up question is that this person's only getting payload size and payload on the client. That is all you get on the client. Payload size and payload. So it's actually fairly... Here, let's just do this in IPython. Import pwn. Okay, so here we do process, or let's say server equals pwn.process. Baby mem. Now the server has launched. Here's one line of the server, right? Cool. Then we do client equals pwn.remote to localhost 1337. There we go. And in the same way, we can still keep reading from the server. Now it's telling us, okay, here we go. Client connection accepted, blah, blah, blah. And then, of course, we can do also client.readline. Oh, client didn't get a read line. Client.clean to read everything. Let's restart because the client doesn't print a new line. That's why it hung. So import pwn server equals, okay, client equals, boom, client dot, so server dot clean, this is everything that the server has printed to us. Cool. Client dot clean, this is everything that the client has printed to us. Client dot send line. And we continue interacting like that. Cool. All right. Awesome stuff. So I think we will stop office hours here. If you have more questions, ask in help on the Discord, and we will help the best that we can. I think that I think we've covered most of the tricks at this point, so that should be good. But yeah, ask on help, and then on Wednesday we start the combo module. It's gonna be awesome. There's a question, are there any levels where we need to leave the canary? Yes, absolutely. All right. Thank you very much, everybody. Thanks for tuning in. See you Wednesday, and good luck. Bye.